In this video, I'm going to go over the solution to Chef and CHGORAM2 from CodeChef February Challenge 2020. So basically in this problem, you're given a tree with n nodes, and you're given a set of the nodes which are suitable, and you need to count the number of triples such that all three nodes in the triple are distinct, all three nodes in the triple are suitable, and for each pair in the triple, the distance is the same. So let's consider a triple which satisfies the conditions in the problem statement, and they all have distance d from each other. Let's consider the path between two of the nodes, and somewhere along this path, they will branch out and reach the third node. And notice that there's a center node which separates all three nodes, and let's call it C. What can we say about the relationship between C and all the other nodes? Well, we can define the distance. We can let D1 be the distance between C and the first node, and D2 and D3 be defined similarly. So we can, after we define these variables, we have the equations as shown below, and we can solve this system of linear equations to find that the distance from each node to C has to be exactly d divided by 2. So this observation will be useful to us later on. So for any triple, there exists a center node such that the center node is equidistant to all of the three nodes. Okay, so for our solution, we will have a DFS function, and when our DFS visits node U, we should count all triples such that the nodes in the triple have a lower common ancestor equal to U. So for example, if we consider the triple here, and this triple has a lower common ancestor, which is U, and we should count the number of such triples when we DFS on U. And notice that we can split the component of this triple into two parts. In the first part, we have the leg, and it's basically just a single extension. And let's call the distance from U to the node A. And in the second part, we have the fork. So basically what it is it starts from U, and it branches in one path until it reaches C. And after it reaches C, it branches out into two different paths. And we'll call the length of the first part of the path B, and for the second part of the path, the length will be equal to D. Now, in order to be able to pair up a leg with a fork, we need this equation to be satisfied. So A must be equal to D minus B in order for the distance of all three nodes to be equal to C. And this leads us to think of a DP solution in order to count the number of legs and the number of forks in a subtree. So we'll let dp1 of u of I be the number of legs starting from node U, such that the distance A is equal to I. And then for the forks, we'll let dp2 of u of I be the number of forks which start from U which satisfy d minus b is equal to I. And of course, now that we have a dp, we need to consider the transitions of the dp. So let's say we transition from v to the node of v. And basically we just add a depth of 1 to the dp. So for dp1, when the depth increases by 1, we go from I to I plus 1 because the length of A here increases by 1. So that's why we add 1 to I. However, for dp2, we subtract 1 because when we go to a parent, the length of B increases by 1, and I is equal to d minus b, so I decreases by 1. So after we change the depth by 1, let's consider how we can merge the dp for the subtree of v with the dp for the subtree of u. And the dp for u is already calculated for the node u and some parts of its subtree. So first we'll consider the new forks, which consist of one leg from the subtree of u and one leg from the subtree of v. And we can calculate this using the product of the dp for the legs. So we have dp1 of v of I ways to choose the leg for the subtree of v. Then we have dp of u of I ways to choose the number of legs for the subtree of u. So in order to find, so the number of new forks will be the product of these two terms. And then for the rest of the legs and the rest of the forks, we simply just add the dp arrays together. Now we also need to calculate the answer while we merge the dp. So remember that a triple consists of a leg and a fork. So we have two cases here. The first case is that the leg comes from the subtree of v and the fork comes from the subtree of u. So in this case, we take dp of 1 of v and dp of 2 of u. In the second case, we take a fork from the subtree of v and a leg from the subtree of u. So we have this product instead. And then we add both of these terms to our answer. Okay, so right now, if we write this dp without any optimizations, then we will have a quadratic solution. One trick that is often used to optimize dp solutions on trees is the merge small to large trick. And we'll use the merge small to large trick on heights in this problem to obtain a linear time solution. So basically the trick says that if we can merge v to u in if we can merge the subtree v into u with a time complexity equal to the minimum height of these two subtrees, then the time complexity will be linear time total. The proof that the time complexity will be linear time is a bit complicated, and I'll include it at the end of this video instead. So I'll include an example of what I mean. So if we merge the subtree of v to u, then we can find the heights of u and v. So for the height of u, it's 1 because there's just one node. And for the height of v, if we also count the parent edge, because we're merging it into u, so if we count the parent edge as well, then we'll have a height of 4. So in this case, when we merge v to u, we should do the minimum of these two heights. So we should do one operation. And next, if we merge a new subtree v, so after we merge the previous subtree, the height of u becomes 4. And we want to merge a new subtree v into u. So we find the height of v, and including the parent edge, is equal to 2. So you want to merge this dp in the minimum of 4 and 2, which is 2. So you want to merge it with 2 operations. So let's look at our transitions and how we can optimize them. So the first transition here for dp1 is that we will turn I into I plus 1. And if we store the dp array as a vector or list, we can think of it as adding a 0 to the beginning of the vector. And similarly for dp of 2, we can think of this transition as removing the first element from the vector. And in fact, we can do these in constant time. If we add or remove from the beginning of the vector, it seems like linear time instead of constant time, but there's a trick which we can use. We can store the reversed vector instead, so that the operations of adding and removing will be on the back of the vector. So the transitions become constant time. So instead of adding 0 to the beginning, we will add 0 to the end. And instead of removing the first element, we will remove the last element in the vector. Now let's look at the second part of the transitions. At first, all of these transitions seem to work in linear time, but for all of the loops which iterate through I in these transitions, we can stop when I is greater than the minimum height of the two subtrees. And this is true because let's say that the subtree of v has the minimum height. Then if we calculate the answer for an I greater than the minimum height of subtree v, then basically dp1 of v of I will be equal to 0, because we can't have any leg which has a depth greater than the height of the subtree. And dp of 2 will also be equal to 0. So the entire sum turns out to be 0, and it turns out that if we consider I greater than the minimum height, then it's pretty much useless. So that's how we can ignore the case when I is greater than the minimum height of the two subtrees. And as for the transition for adding the rest, if v happens to be the subtree with the minimum height, then we can just do the same thing over here, and our time complexity will be good. But otherwise, if u is the minimum subtree, then first we need to swap the dp arrays of u and v before merging them. So now I'll explain my code for the solution. So to start with, we start by initializing dp1 and dp2. So at first, the subtree of u is just a single node containing the node u. So we'll have a leg if u is suitable and we don't have any forks. And now for each child of v, we will call dfs on v. And after we call dfs on v, want to merge the DP for v to u and update the answer. So the first thing we do is we take the DP of u and we increase the depth by 1. So this is the first part of the transition that I said here. And since we store the reverse vectors, instead of adding 0 to the beginning, we add 0 to the back. And instead of removing the first element from the vector, we remove the last element of the vector. So these are both in constant time, which is good. And now we move on to the second part of our transition. So first, we'll make sure that if the DP of v has a greater height, then we'll just swap these two arrays. So then we can guarantee that DP of v has the smaller height. And then if DP2 of u is smaller than, if the size of DP2 of u is smaller than the size of DP1 of v, then we can simply add zeros to the end of DP of u. But remember that we stored DP2 of u in reverse, so instead we insert the zeros to the beginning of DP2 of u. And then this part also works in the minimum. This part works in at most the size of DP1 of v, which is the minimum height of the two subtrees. And then after we switch the DPs to make sure that DP of v has the smallest height, then we'll update the answer. So basically we just consider our two cases over here. The first case is we have a leg from v and we have a fork from u. And basically just iterate through all the possible I. And then we multiply the DP values together and we add them to the answer. And remember that our DP vectors are stored in reverse. So that's why in order to access the value of the DP, I take the index and I subtract the index from the size of the vector. And then I do the same thing for the second case. And now after I update the answer, I combine the DPs together. So the first thing I need to do is calculate the number of new forks. So basically we just use this formula over here. And we add the product of DP1 of u and DP1 of v into DP2 of u. And then we just add the rest together, which is straightforward as well. So that's basically it for my code. And the last thing we need to do is to prove that this solution runs in linear time. So when we merge the subtree v to u, let's color the deepest path of the minimum height subtree between u and v. And if there are multiple deepest paths, then we will choose the leaf with the smallest index in order to break ties. Okay, so in this case, the height of this subtree is 2 and the height of the subtree is 1. Oh wait, the height of this subtree is 3 and the height of this subtree is 1. So the minimum height subtree will be u. And then since we color the deepest path of the subtree of u, but there's no path, so we basically don't do anything. So we merge it, and then let's say that u has another subtree v. And then the height of u is equal to 3, and the height of v is equal to 2. So we color the deepest path of the subtree of v, which is this path over here. So we color this edge. Okay, so let's take our previous subtree. Now the previous u becomes v, and we want to merge it into another subtree. And then basically, the minimum height subtree, as we can see, is v. So we color the deepest path of the subtree of v, which consists of these three edges here. So we can continue working with other small samples, but we can realize that when we use this process, we seem to never color the same edge twice. And we can reason why this is the case. So let's say that we merged u into another subtree, and why won't we color these edges ever again? We won't color them again because these aren't the deepest path anymore. The deepest path of subtree u will be this path, so these won't be colored. So in fact, whenever we merge v into u and then we color the deepest path which is colored will not be the deepest path anymore. So that means we will never color it again. So notice that we have at most we can color the edges at most O of n times. And when we merge u to v, we color the O of the minimum of the height of u and the height of v edges. So when we optimize our DP with this merge small to large trick on heights, and when we do our DP transitions with this time complexity, we know that we will basically process at most O of n edges. So the total time complexity is O of n.